Hi everyone, I'm Adam Richie-Halford. This is my first time at SciPy, and therefore it's my first SciPy talk. If you want to follow along, there's a URL along the bottom there. But before I start, I just want to take this opportunity to thank the sponsors and the organizers of the conference, and especially the reviewers. If you reviewed for any talk or paper, not just this session, thanks. I appreciate it. I know that the other presenters do too. One of the things that I love about Python is its ability to enable domain scientists to rapidly transition their expertise into research computing. I think SciPy is a big part of that. And yesterday's keynote, Ralph talked about, hopefully that'll come up again. At yesterday's keynote, Ralph talked about the importance of simplified APIs in enhancing the accessibility of Python. And I want to introduce Cloudnot, which is a library that we wrote that I think nudges that conversation forward a little bit in the realm of cloud computing. Okay, so who are we? What do we do? My collaborator on this project is Ariel Roquem. He is a senior data scientist at the eScience Institute at the University of Washington. That's one of those Moore Sloan data science centers that Tracy talked about this morning. He develops open source software for neuroscience. He's a carpentries instructor and an instructor trainer. And he's also the chair of the eScience Working Group on Reproducibility and Open Science. I'm Adam. I'm a PhD candidate in the physics department at UW. So on the physics side of things, I do quantum Monte Carlo simulations of neutron matter. I also collaborate with Ariel on visualization tools, machine learning tools for neuroimaging. And I'm also a carpentries instructor. So we use Python a lot. I use it in my physics research for post-processing of my Monte Carlo samples. Ariel is a core contributor to DiPi, which is a computational neuroanatomy package. He's also the lead developer of PIAFQ. I've contributed to PIAFQ. Which is a white matter tractography package that I'll actually return to later in the talk when we go over some examples. So this is all just to convince you that we love using Python. We're very happy in our Python environment. We're comfortable in it. This is an example of some PIAFQ diffusion MRI studies in the Jupyter Notebook. We love it there. If we could do all of our computational workload from within, a Python IDE or Python console or Jupyter Notebook, that would make us very happy. But we also really like to use AWS. It has some distinct advantages. A lot of the applications that we use can achieve linear scalability if we just throw more EC2 instances or spot instances at them. It's elastic, so we pay for resources when we're using them, and we don't pay for them when we're not. And it gives us the ability to handle large data sets, much larger than we could do on our local machine. But of course, the pros column is shifted to the left there, so you know what's coming. It has some disadvantages. There's a bit of a learning curve. You have to learn some new terminology. You have to learn all about AWS's services and how they interact with each other. It can be difficult to choose the right or appropriate instances, and I'll talk about that a bit more in a second. And of course, there's additional overhead in provisioning your own resources on AWS. So I talked about choosing the right instance. This is EC2 Instances.info. It's a website that bills itself as the easy Amazon EC2 instance comparison tool. And it's 4 pages there. Okay, so Tracy gave a great keynote this morning, and she talked about how sometimes introductory experiences in computing can be disempowering. And I can speak from personal experience when I say that sometimes introductory experiences in cloud computing can be really disempowering, and they can scare some people away. Ariel and I are both carpentries instructors, and so what we wanted to do with Cloudnot is use some of the knowledge that we got from the instructor training about cognitive load and apply that to an API that gives researchers access to AWS tools, but lets them do it in a sort of comfortable way from within their Cloudnot environment. So yeah, that's the challenge. Reap the benefits of AWS, all from within the comfort of our Python environment, or if you're a Tolkien fan, have an adventure without leaving the Shire. So there's our little Hobbit Home We can use Python in there. We can eat our 7 meals a day, and we can have a great adventure without having to go deal with a dragon or wear a ring. I should say that there have been previous attempts at this sort of thing. PiCloud is a package that was written in 2010. It was acquired by Dropbox in 2013. And as far as I know, it's moribund. I don't know what happened to it after 2013. If anyone does, please tell me. Pywren was introduced last year. Eric Jonas from the Rise Lab gave a great talk about it at AnacondaCon last year. It's a major source of inspiration for Cloudnot, and you'll see that when I talk about the API. But it's built on top of AWS Lambda, and because it's built on Lambda, it has some limitations in the types of jobs you can run. Namely, you're limited to 5-minute execution time, 1.5 gigs of RAM, 512 megabytes of local storage, and no root access. So there are computational workloads that fit within those limits, but there are also a lot that don't. So instead, we built Cloudnot on top of AWS Batch, which is an AWS service that tries to abstract away all of the infrastructure details. Instead of saying, I want these types of instances, with this much memory and this many vCPUs, you define jobs, and you define the constraints that your jobs need, and you say how many you want, and then AWS dynamically provisions all of the resources to satisfy those job constraints. And this is sort of a tagline that they have on their advertisement stuff, but it really does allow scientists to run hundreds of thousands of batch jobs at once. It's kind of impressive. But it has some cons. You can submit jobs through the AWS web console, so that resists automation. It does require learning some new terminology. Even with all the great abstractions that Batch introduces, you have to learn what a compute environment is and set up job queues and learn how to define these jobs. And it doesn't easily facilitate reproducibility and scripting, mostly because you're using the web console. So I want to walk you through the Cloudnot API and show you how simple it can be. And in order to do so, I want to do it with this sort of pedagogical example, estimating the value of pi using Monte Carlo methods. So we're going to basically throw a bunch of darts at this square. If they fall within that quarter circle, we're going to say it's a hit. And if they don't, we're going to call it a miss. And the ratio of hits to attempts will be related to the value of pi. OK, so I import Cloudnot. I need to define my user-defined function, or my UDF. Here it's Monty PyCount. One thing that I should note, kind of a quirk of Cloudnot, is that you should import your dependencies within your function. I know that's stylistically frowned upon, but Cloudnot uses this package called piprex to read the user-defined function and introspect any software dependencies from it. So it's what we got. After defining your function, you pass it to the main object in Cloudnot, which is called a knot. And this is a blocking call. It will create all of your resources on AWS. It creates the compute environment I was talking about, the job queue, job definitions. It Dockerizes your UDF. I'll go into some of the details in a minute. Once that returns, you can pass arguments to the map method. So here, in this example, each job is going to take 10 million samples. I'm running 1,000 jobs, so we're going to get 10 billion samples to estimate pi. And then I create an array of length 1,000, one element for each job, and each argument is 10 million because I want each job to generate 10 million samples. And then I just pass that args array to the not.map method. Cloudnot is built to mimic Python's concurrent futures executor objects, so it returns a future. And if you've used futures before, then all of the methods should be familiar with you. While you're waiting, you can use not.viewJobs to get a nice summary of your jobs if they're pending or submitted or running. You can check if they're done by using the future.done method. You can get the result using the .result method. That takes an optional timeout argument. So if you don't want to wait forever for it to return, if you only want to wait a minute and then get some sort of timeout error, you can do that. If you happen to say later, well, future equals 1 or something and lose your future, that's fine. The not keeps track of all the jobs that it has submitted in the past. So this highlighted line is equivalent to the one above it. And because we're using concurrent futures, you can attach callbacks to your results. So in this example, my Monty PyCount function, it only returned the number of non-zeros. I actually want to divide by the total number of samples to get my estimate of pi, so I'm attaching this pi from future callback, which adjusts a global pi variable. So I want to talk about what that workflow would have looked like without Cloudnot if you wanted to use AWS Batch. Well, first, AWS Batch uses Docker images to define its jobs. So you would have to build a Docker image of your command line interface version of your function. That's done on your local machine. You create an Amazon ECR repo, maybe using the web interface, or maybe you use AWS CLI for that. You push your built image to ECR. You create all the necessary resources on Amazon, your IAM roles, a VPC, gateways, security group, compute environment, job queue, all that. I'm intentionally making it sound like it's way, way harder than it really is. You create a job definition that points to that Docker image so that all of your EC2 jobs know what job to run. And then finally, you submit jobs using the web interface, using those arguments. Okay, so that's what the API looks like. I want to talk very briefly about what's going on under the hood. This is batch computing, so Cloudnot uses a single program, multiple data paradigm for parallelization. Once you instantiate this not object, what's going on under the hood is that Cloudnot sends the UDF, it wraps that in a CLI, Dockerizes it, and then sends it up to Amazon ECR. That's what's going on the left side of that figure. And then on the right, while it's doing that, it uses a CloudFormation template. How's the resolution on that? Can you guys see any of that? It's a little too small, isn't it? Okay. Okay. Well, yeah, it's online, so you can check it out later. But I'll talk through. It's using a CloudFormation template, and it's creating all those resources that I said you need. And then everything is internally consistent, so the job definition knows where your Docker image is located, and AWS Batch is able to manage all of your EC2 instances. That's the single program, and then for the multiple data, when you use the map method, map traverses the outer dimension of your argument array or argument sequence. It doesn't have to be an array. Serializes that input, sends it to S3, again in a way that's internally consistent with all the other resources on AWS. And then those EC2 instances can retrieve input from S3, process, store output on S3, from which not.map can actually retrieve the results. Okay, so that's a bit of how it works. I want to go over some examples. This first example is sort of a pedagogical example. We're just going to solve the steady state 2D heat equation. If you don't like the equation, that's fine, you can ignore it. We're trying to find the temperature on that plate after a long time, just holding the temperature on the perimeter under certain constraints. So you can think of two different ways to benchmark that. One is to pretend that, okay, you're really interested in the temperature if you hold the bottom edge at 1 degree or 2 degrees or 3 degrees, and for some reason you're interested in a bunch of different constraints. You can parallelize over the constraint set. That's what we do in this chart. You can see an increasing number of arguments on the bottom and time on the y-axis. We benchmark Cloudnot, well, two configurations of Cloudnot against pywren, and the clear winner here is pywren. It's got basically constant scaling from like 2 to the 2 to 2 to the 9. And then for larger arguments, both Cloudnot and pywren exhibit linear scaling with kind of a small coefficient. I can speculate a bit more about this scaling, but I'm a little worried about time. So if you're interested, find me later, and we can talk about it. But there's another way that you can explore this parameter space. You could also imagine increasing the system size. Pretend that a 10 by 10 grid just isn't going to do it for your project. You want to increase the system size and get really high spatial resolution on your surface. Well, at some point, you're going to get a grid that's large enough that you're going to either exceed that the RAM requirement for the RAM limitation on Lambda, or you're going to exceed the execution time limit on Lambda. And that's exactly what happens here. You reach that grayed out area, and that's the Cloudnot only area where pywren it gives you an error. Okay, so the takeaway there is that if your UDF fits within Lambda's limitations, you should probably use pywren. But if not, Cloudnot's here for you. You can use that. That was just sort of a pedagogical example. Here's something involving actual real science. PIAFQ is a package that takes raw diffusion MRI images, like you'd see on the left, identifies regions of interest within the brain, and then tracks long-range connections in the white matter between those areas to come up with tractometry data like you'd see on the right. Ariel previously studied the performance of Dask, Myria, and Spark on exactly this problem. And since that data was already there, we thought, okay, well, let's throw Cloudnot at it and see how it performs. So for a small number of subjects, Cloudnot does not compete at all with Dask or Myria or Spark. This is a log scale on the y-axis. But as we increase the number of subjects, it starts catching up. It's about 10% slower than Spark and Myria, and about 25% slower than Dask, which is the winner at the high end of the number of subjects there. So the takeaway there is that, yes, Cloudnot is slower. However, that previous study that Ariel did with a team of 4 other grad students and postdocs in CS took them 6 months. Now, admittedly, some of that 6 months was, to make sure that they were rigorously comparing apples to apples. But the Cloudnot implementation took Ariel a day, an afternoon, actually. So our proposition is that for a lot of computational workflows, that's an adequate trade-off. So Cloudnot favors workloads where your development time is way more important than your execution time. Okay, microscopy data. Here's thank you. Another example, the MRI example demonstrates Cloudnot's use on large data sets. The microscopy example demonstrates Cloudnot's use on very complicated software dependencies. There's a lab at UW called the NANS lab. They are interested in the mobility of synthetically designed nanoparticles in living tissue. So what they do is they take essentially movies of microscopic images. So you have very high spatial resolution and very high temporal resolution. And the software that they use to do this is, it's called TrackMate. It's based on ImageJ, and both of those are written in Java and can be scripted with Jython. I think if you tried to include these dependencies using pywren or well, actually, we just had a talk on how to get dependencies easily in your EC2 instances. You would have to do some setup. But luckily, since Cloudnot is built on top of Docker, you can do that easily in a Docker file. You can just write wget and get the software that you want. As I mentioned, these are also pretty large data sets. So in this case, we had to use a custom AMI to include a larger volume because the default batch AMI is limited to 30 gigabytes. And these were all things that we could do using parameters in the not object. Well, in the AMI data case, in the AMI case, that's what we could do. In the Docker case, we used Cloudnot to create the Docker file, and then we went in and added the wget lines. So the takeaway here is that we did have to do some trickery to get the software dependencies to work. This led to longer development time. Ariel had to sit down with Chad Curtis, who was the sort of lead on this project, and talk him through, what's an AMI, how do you adjust your Docker image. But now this lab has completely transitioned from using this bespoke local cluster to using AWS. When they onboard a new grad student or a postdoc in their group, they don't have to know about Docker They don't have to know about AWS. They can just do their science. So yeah, this is sort of like referencing Tracy's talk about the Wonder Woman. It's great if you are a data science Wonder Woman, but you shouldn't have to be in order to run your science at scale. And this is also a great example of capability computing, whereas the MRI example was a capacity enhancement. People could do more work more quickly. In this case, those lab members have told us they're asking different questions now because they're able to have more compute power. So they're actually addressing new capabilities with their software. Yeah, okay, so Cloudnot favors workloads where development time matters more than execution time. I think a lot of data science work fits within that. A lot of ETL, exploratory data analysis, parameter sweeps fall within that. And the simplified API makes cloud computing more accessible. You really only need to do 3 things: import, instantiate a knot, and then use the map method. I'd like to encourage you, especially if you onboard, grad students or postdocs or new people, and you don't want them to have to learn a bunch about AWS, give Cloudnot a spin. Please try and break it, and submit issues and contribute if you want. With that, I'll take questions.
Thank you. Hey, thanks for the talk. Really good. Question for you is there any way in Cloudnot to be able to access previously defined user-defined functions so that you can reuse them? It's kind of one of the benefits of like AWS Batch is I've got algorithm A up there and maybe I want to run it on Monday, Wednesday, and 3 years from now. Or is it kind of more like per instance of like per script is kind of how it has to work?
No, you can definitely save previously defined functions. So I didn't go too much into this, but Knot has a clobber method that will basically destroy all of your resources on AWS. It'll also destroy the Docker image on ECR. If you don't clobber, then you can keep that Docker image on ECR, and then instantiate new knots. And then in another Python session, you can come back and you can say, hey, I want to use that again, and it'll retrieve it quickly.
So Knot has an API for viewing the Docker images that are already on AWS and saying, hey, select image 4 and use it.
Yes, yeah,
sort of. Okay.
It does, sort of. It's not very intuitive right now, but one of our future plans is to make that more intuitive. But to answer your question, if you use the same name or ECR like ID, then it will retrieve it.
Okay. And then my second question was just on AWS permissions. Is there any way to sort of provision that, like per script, per whatever? Or is it just going to look into like your local credentials that you have saved in the environment?
Yeah, that's a good question. The permissions model is one of the most confusing aspects of AWS. Cloudnot basically just assumes that you have all the permissions that you would need to run AWS Batch through the console. And in the Cloudnot documentation, we list the minimal permissions necessary in a JSON file. You could also adopt roles to do Cloudnot jobs and have your administrator manage those roles. So far, we've tested Cloudnot with kind of small research groups in which people were very permissive with what you could do. If anyone wants to use it in a larger setting, where you actually have someone who's like the AWS administrator, come talk to me. We're happy to work on development in that aspect.
Use them as a guinea pig. Questions? We've still got plenty of time.
Hi, Adam. Thanks for the talk. So I have a question about, I've got applications that do a lot of reading and saving to disk of CSVs, sort of mid-execution. Mm-hmm. Does Cloudnot support that sort of operation?
Okay, so you want to save state basically in between Cloudnot sessions?
Well, sort of doing many runs, and every time you start a run, it loads a bunch of config files from a CSV.
Yeah, so, I mean, I think the way that I would approach that would be to store some stuff on S3, and then have each instance retrieve from S3. And the nice thing about that is that if your instances are co-located in the same data center as your S3 buckets, you don't pay for that transfer within the data center.
Does that function the same way with Batch as it does with EC2?
I'm sorry?
Does it function the same way with AWS Batch as it does with EC2?
Yeah, so sorry if I didn't make this clear. Batch is just a service that manages your EC2 instances. And what you're actually paying for is just your EC2 time. There's no cost to the batch overhead.
All right, that makes sense. Thanks.
Yep.
Stupid question from the chair. Well, you did your import within the function there. So is pip or the backend that you're running with dynamically installing things via pip by trying to resolve the name? So if I have a package that I know is pip installable, but not installable, not part of the core SciPy ecosystem, it'll actually go and automatically try and install them.
Yeah, well, so it'll give you a warning if you have import statements that don't match what pip can install, and then not accepts other arguments where you can provide, for example, if you want a pip install from a GitHub repo, you can provide that GitHub address. And if that still fails, then Cloudnot, it'll give you a warning and it'll say, hey, I don't know how to install this stuff. Here's the location of your Docker file. Go add lines to it.
Right. What does it use a basic Python distribution, or does it actually sit on top of something like Conda on the cloud?
I don't. It uses
whatever's coming with the normal batch instance or the normal.
Oh, well, so right, yeah, it's a sort of the default batch Linux AMI, but
cool.
But the package that we rely on is called piprex, and I don't actually know the internals of how piprex works for that.
Related, sort of offside question. What about the licensing? What open source license are you using for this?
This is MIT. Are you asking about Cloudnot specifically? Yeah,
Cloudnot.
MIT.
All right, awesome, thank you.
Simple question. We've got time for one more question.
Oh, I buried the lead. I'm sorry. A knot is a collective noun for snakes. So, like you can have like a murder of crows or otters, or you can have a raft of otters. Anyway, you can have a knot of snakes.
And on that note, we'll move on to our next talk. Thank the speaker again, please.
Thanks.